Last thing we're going to do this week is take a look at how we can extend these vector operations to larger matrices. So the basic functions that we talked about, like addition and scalar multiplication, just are straightforward. You can add any two matrices of the same shape just by summing their elements, and you can multiply a matrix by a scalar just by multiplying the scalar by each element. So nothing too new here. We can also transpose any matrix, just like we did with a vector. So what we do is we just basically switch the indexes around. So we take, if we transpose matrix A into A prime or A transpose, then Aij equals A transpose Ji. So here's an example where we have a matrix that's 3 by 2. We transpose it into a 2 by 3 matrix where the first row is equivalent to the first column of the original matrix. So the matrix product is a generalization of the inner product we've already seen. And essentially the idea is that two matrices can be multiplied if and only if the first one has the same number of columns as the second one has rows. So I'm going to put this another way. If one matrix is shape n by k, it can be multiplied by any matrix that is of shape k by p. So they have to have the same number. The first matrix has to have the same number of columns as the second matrix has rows. The result of this multiplication will be a matrix that has the same number of rows as the first and the same number of columns as the second, or in this case, an n by p matrix. Note that order matters when multiplying matrices, and that any matrix can be multiplied by its own transpose. And this is also why we transpose vectors in when we take the inner product, because we want them to have the same number of, we want them to be, we want the first one to be a 1 by k and the second one to be a k by 1. That way we get left with a 1 by 1. So to compute a matrix product, let's think about two matrices, A, which is n by k, and B, which is k by p. Their product AB will be an n by p. And each cell, which we denote ABij, will contain the inner product from row I of A and column J from B. So this gets a little bit difficult to track in your head. And can be a little tedious, but we got to do it. So let's work on an example to hopefully help. So let's call matrix A this first matrix and matrix B this second matrix. So what are the dimensions of these matrices? So the first one is 2 by 3. The second one is 3 by 1. Can these matrices be multiplied? Why or why not? The answer here is yes, indeed, because A has 3 columns and B has 3 rows. So A has the same number of columns that B has rows. What will be the shape of the resulting matrix? This will be 2 by 1, since A has 2 rows and B has 1 column. And so now that we've established all that, let's get to work. So what is AB11? So AB11 is the inner product of the first row of A and the first column of B. So we take the first row of A, which is 3, negative 1, 2. So you see that gets put over here. And then the first column of B only has 1 column. So the first column is just that. And so we take the inner product of these two. It turns out that's 5. So that's the entry for AB11. What about AB21? So we basically do the same thing. We take the second row of A. And again, we take the first column, the only column of B. We get their inner product, and that gives us 69. And that gives us this matrix, this 2 by 1 matrix with elements 5 and 69. So let's try another one. We'll keep A the same as before, and we'll define a new matrix C. Can we multiply AC? Why or why not? In this case, we can't, because A has 3 columns and C has 2 rows. So these are not conformable matrices. What about if we flip it? Can we do CA? That works. C has 2 columns, A has 2 rows. We can do this. And so what will be the resulting shape? The resulting shape will be 2 by 3 because C has 2 rows and A has 3 columns. So we know we have a 2 by 3 matrix, and let's fill in a couple pieces. So what's CA11? What pieces do we need? We need the first row of C and the first column of A. So I put them in here, but let's go back and look. So the first row of C is 2, 0, and the first column of A is 3, 1. So that's what we have here. And so we get this inner product, which we do down here. And that gives us 6. So CA11 is 6. Let's try one more. We'll skip over to CA13. What pieces do we need? We need the first row of C and the third column of A. So that's once again, the first row of C is still 2, 0. The third column of A is 2, 4. I'm not going to go back, just take my word for it. So we multiply this out and we get 4. And here for reference is the rest of it. You will have to do a little bit of matrix multiplication for the assignment. You don't have to write out this part necessarily. You probably should write out something like this. I mean, one way or another, you have to show me that you're doing the right multiplications. You can't just do this in R. You have to show some level of work, but you don't have to be quite as detailed as this. This is partly just to make it hopefully easier for you to see. But as long as you show me that you're doing your work correctly and that you know what the procedures are, you'll be good. So we can do this in R. To make a matrix, there are a bunch of different ways we can create a matrix in R. So we can use cbind to combine several columns, or rbind to combine several rows. So I like to use, I prefer to use rbind because it's just how my brain thinks. So if I wanted to create this C matrix, I could do rbind of this 2, 0, and then 1, -1. You see that gives me this matrix I wanted. Don't name things to little c. C is a concatenate. Don't do that. T is a typo. Ignore that. So for cbind, you can also, cbind allows you to combine several columns. So here, the first column is 2, 1. The second one is 0, -1. That gives you the same matrix. You can also use the matrix function where you just enter one string of numbers. And then you specify the number of rows and columns. Note that if you do this, R is going to assume you're going column-wise. So down here you see I don't specify by row equals true. I need to specify 2, 1, which goes in the columns, and then 0, -1, which goes in the next column. And then I say I want 2 by 2. If you specify by row by true equals true, it'll go row-wise instead. So 2, 0, 1, -1. All of these produce the same matrix, so any of these would be valid. We can use the special operator in R with the parentheses and the star to multiply matrices, just like we did vectors. So I already made C, now I'm going to make A. And now I can multiply C by A, and we see we get the same result as when we did it by hand. So this is a good way to check your work. And when you're doing this in real life, you will probably just do it this way. The identity matrix is another special matrix denoted by capital letter I. It's a symmetrical matrix, which has ones along the diagonal and zeros everywhere else. So a 3 by 3 identity matrix would look like this. This is actually incorrect. This should be a 0. I forgot to reproduce these slides when I started recording. So the correct ones will be on Blackboard, but this one here should be a 0. It should be all zeros off the diagonal and then ones along the diagonal. So the identity matrix has many uses. It serves a similar role to the number 1 in ordinary algebra. So for example, note that a 3 by 3 identity matrix multiplied by any other 3 by 3 matrix in any order, this is a special case where order doesn't matter, reproduces the same matrix, just like multiplying any number by 1. So I times A equals A times I equals A. So again, the identity matrix reproduces the same matrix. One use of I is to help define the inverse of a matrix. We say that B is the inverse of A if B times A equals A times B equals I. We can also denote the inverse of A as A to the -1. Unfortunately, computing the inverse of a matrix is not very easy to do by hand. We're usually just going to rely on a computer to do it, but we can do it for a 2x2. That's within our grasp, and we're going to practice that so you can see what it looks like. Before we do, we have to learn about one other special property of square matrices, the determinant. The determinant is a special number that plays an important role in many operations that involve square matrices. We denote the determinant of a matrix, of a square matrix specifically, as using these vertical bars, almost like the absolute number symbol. One of the reasons the inverse is difficult to compute for large matrices is because the determinant is as well. It's also difficult for other reasons, but the determinant is also difficult to compute for larger matrices. However, it is also fairly straightforward for a 2x2. So for a 2x2 matrix, the determinant is equal, so if we name our matrix A, the determinant of A is equal to A11 times A22 minus A12 times A21. So if we define the following matrix, what is the determinant here of A? So remember, it's A11 times A22 minus A12 times A21. So that's 1 times 4 minus 3 times 6, which is negative 14. So the determinant of this matrix is negative 14. We can use the det function in R to get the determinant to check our work in this case of any square matrix. So here I make my matrix, I check the determinant, I get negative 14. We can do this for more complex matrices, of course, if you ever need the determinant, which you don't often need it unless you're programming something. It's used for a lot of things, but usually in the back end, when you're doing a lot of functions in your software, the software is getting the determinant somewhere, but you don't see it. But here we can get it with the det, and we see for a 3x3 matrix, it's negative 222 for this 3x3 matrix I defined here. So back to inversion. For a 2x2 matrix, the inverse can be computed as 1 over the determinant of the matrix times this sort of rejiggered version of it, where A22 is the first element, negative A12 is the second element. So the first row is A22, negative A12. The second row is negative A21, and the the second element of the second row is A11. So as we defined it before, let's find the inverse of A. So just to refresh you, our matrix before was 1, 3, 6, 4, going row-wise. So here we need to flip it around like this. So we take 1 over the determinant, negative 14, times 4, negative 3, 6, 1. And that gives us this here, negative 4 over 14, 3 over 14, 6 over 14, negative 1 over 14. That's our inverse matrix. To verify that it's the inverse of our original matrix, we can multiply them together. Remember, we can do this in any order. So here I'm taking A times A to the negative 1. And if we do this, so we're going to take 1 times negative 4 over 14, and then 3 times 6 over 14. That's going to be our first element because we're doing our matrix product. So that's going to give us negative 4 over 14 plus 18 over 14, and that's going to give us 1. And then so we are going to do 3 times the second row, 6, 14. So it's 1 times 3 over 14 and 3 times negative 1 over 14. So that's 3 over 14 plus negative 3 over 14, and it's going to give us 0. And if you can verify the rest of this, this does reproduce 2x2 identity matrix. And again, we can check our work in R. So here I'm just going to call A my original matrix. I'm going to call A inverse as I computed it here. And then we're going to multiply A times A inverse. We're going to get the identity matrix, and we can go the other way. We can multiply A inverse times A. We still get the identity matrix. We can get the inverse of a matrix in R if the inverse of a matrix exists. And we do that with the solve function. So here I'm going to get A inverse again by computing solve A. So we see that it gives us this thing. And then if I reprint out A inverse, which remember I entered this as fractions here, R is going to print it out now as decimals. We see we get the same thing. So that's how you can get A inverse in R. So the last thing we're going to talk about today is an orthogonal matrix, which is a special matrix whose transpose is also its inverse. So A transpose equals A inverse. So another way to think about this is that A transpose A equals A times A transpose equals the identity matrix. So it's a special square matrix, of course. So here's an example of an orthogonal matrix. Let's verify that it's orthogonal by multiplying it by its transpose. So transposing this matrix, we get our original matrix here. We transpose it. It just winds up flipping the negative 28 and 28. So we get 0.96 times 0.96 up here, and then negative 0.28 times negative 0.28 down here. So we're just squaring these elements here. And so that's going to give us 0.92 plus 0.08. That's going to give us 1. So then we'll do the second one. We'll do 0.96 times 0.28 and negative 0.28 times 0.96. So 0.96 times 0.28, negative 0.28 times 0.96 gives us 0.27 minus 0.27 gives us 0. And again, I'm not going to go through every step, but you can verify this reproduces an identity matrix. And we can, again, verify this in R. So I'm going to create this matrix, and then I'm going to multiply it by its transpose, and we see it gives us the identity matrix.